Hi, we meet again today. This time we would like to discuss about feature extraction. This is the last part for our discussions on image data. We will start with the feature or the definition of the feature itself. But before that, I would like to let you know that we are using the same textbook as the previous meeting. First is the digital image processing by Gonzalez and Woods, published in 2018, and computer vision algorithms and applications, published in February 2021, written by Selsky. Feature is something that is distinctive of individual image objects or entire images, in the sense that we don't have objects or many objects in one image. So feature is required when we want to label objects, in which case we have so many objects in one image, and to distinguish one image from another if we consider the image as the object itself. So the features could also be regarded as attributes that are going to help us assign unique labels to objects, such as motorcycle, car, and so on, or more generally are going to be of value in differentiating between entire images or family of images. We have a number of aspects for features. So we could distinguish the major category into two, that is feature detections and feature descriptions. Now take an example that we are considering object corners. Feature detection refers to finding the corners in a region or an image, whereas the feature description refers to assigning quantitative and sometimes qualitative attributes to the detected features, such as corner orientations, locations, and attribute that describes the characteristic of the corner itself. So feature detections is normally the prerequisite for feature description. Now we want some characteristic on the features that we extract from the image. For example, we want to have feature which is invariant under some geometric transformation. Area, as an example, is invariant under translation, rotation, and reflection, whereas area is covariant under scaling, meaning that an area of an object will not change the value if the object is translated, rotated, or reflected. But the area of the object will change the value if the object is scaled. It could be because the object is going further, like a car traveling further from the camera, or on the other direction, a car is coming to the camera. Now, it could also be caused by zooming of the camera, where the object is actually at the same distance. Now, we could distinguish features also as local features or global features. Now, global features could be meant or interpreted as the features obtained from the entire image, whereas local features could be interpreted as the features extracted from parts of the image, such as the corner that we have discussed before. Now, on other example, we could say that local features could be a volume of a liquid of a bottle in a bottling inspection, for example, whereas the global features means the total volume of bottles per day processed by a certain machine. Now, from the categorical point of view, we could distinguish features as coming from the boundary of the object, the region of the object, and the whole image. So we will continue our discussion with these categories. We start with the boundary categories, and then we'll continue with regional features, and then we will close our meeting with the whole image features. Okay, so we start with the boundary and here, and then followed by the region, and then the whole image features. Now we start with the first representations, which is the Freeman chain codes. Figure 12.3 from textbook number 1 shows the direction numbers used in the Freeman chain code. We could use either 4 directional chain code or 8 directional chain code. In a 4 directional chain code, the direction is labeled by number from 0 to 3, whereas in the 8 directional chain code, the direction is numbered from 0 to 7. Now here is the example of the Freeman chain code. We have the object on the left here. If we take the chain code directly from the pixel level boundary, then the number of the chains would be very high, thousands, even 10,000 or so. So what we normally do is to resampling the boundary or resampling the object so that the resulted boundary will be low in number, let's say 10, 100 also. So then we have the picture on the middle here as the result of the resampling or downsampling, and then we encode the number. Let's say we start from this position, which is that position. We are traveling onto the clockwise direction. So the code would be the horizontal is 0, and then on the southeast, the direction number is 7, followed by on the south direction, which is 6, followed by 4, and so on. So the chain code would be 0, 7, 6, 6, 6, 6, 6, 4, 5, and so on. Okay, this is a more realistic example of how we extract the Freeman chain code. So we start with the object on the top left corner, and then we smooth the object using the box kernel or averaging kernel of size 9 by 9. Now for different situations, we might need different size of the kernel. So the result is a smoother image, which means, or at least we want it to be having less noise. And then we threshold the image using Otsu. We have discussed this one also. So then we have the boundary. But the boundary is thick, so we process further to thin our boundaries by taking only the outer part of the boundary. So we have this, which is the outer part of the boundary, and then we do the downsampling. Let's say we could resample using a grid of size, let's say 4 by 4 or 5 by 5 or 8 by 8 pixel. Then we have the boundaries, and so we generate the chain code from this object. So if again we start from the top left corner, then we will have direction of 0. So we have a 0, 0, 0, and then 6 here, and then we have 0 again, going east and then going south for so many times. So we have then 6, and so on until ends at 0, 2. Okay, since the chain codes reflects the direction when we traverse the boundary, so in order to be invariance under rotation, now we take the difference of the changes. So we don't take the chain code itself, but we take the difference of the chain codes. Now if we start from this position, takes the difference with the next chain code, then from 0 to 0 the difference is 0. Okay? And then from 0 to 0 again the difference is 0 again, and then from 0 to 0 again the difference is 0. Next we have from 0 to 6, and the difference is 6. Okay, so 0 to 6, okay, yeah, the difference is 6. When we calculate the difference, we go on the anti-clockwise direction. Okay, we will see again the detail later on when we discuss the ship number. We now see different kind of chain codes. We start with an object. It is a curve, almost like an S. And then we determine a line segment, and the length of the line segment determine the accuracy or the precision of our approximation. So let's suppose this is the length of the line segments, which is the radius of the circles that is used here. So we start from the beginning of the curve, draw a circle with the radius of the line segment length, and so we have the circle cross the curve, and that intersections, and then we join a straight line from the end of the curve to the intersection. And then we look at the table here. What is the direction? Okay, so we could start from the direction. So in this case, the direction is 0.12, which is somewhere around here. Now the picture itself represents only some direction. We could be much more detailed than that. And then after we have the first segment, we go to the second segment by drawing another circle with the center here until the circle intersect with the curve, and again we connect the end of the previous segment with the intersection. So we obtain the second segment. Now we could again we could do what we have done before with the previous chain code. We code the absolute direction of the line segment. Then after that, to overcome the problem of the rotation of the object, then we continue with taking the difference of the chain codes. Okay, the next features is what is known as a signature. Now, one way to obtain a signature of an object is by drawing a function of the distance between the means or the center of the object and the boundary. So for the first object, which is a circle, now the center is there and the boundary happens to be a circle. So the distance between the center to the boundary is always the same regardless of the angle. So our plot is the angle. This is the angle theta, and the distance is the vertical axis, which represents the distance from the center to the boundary. So for a circle, the signature is a straight line, whereas for a square, the signature is a wave with 4 peaks there, which represent the corners of the object. So then we will continue later on. We could use this as the signature of the object, and we could also calculate other values which will represent the signature. For example, is the second order moment, third order moment from this signature. So it's depend on what we need. Okay, and this is just another example of a signature. We have two regions, which is almost like a triangle and almost like a square. And so we do some pre-processing to obtain the boundary. And then after we obtain the boundary, again, we calculate the center and then create the signature starting from, let's say this, from the horizontal, and then going anti-clockwise, and then we plot the angle with the distance of the center to the boundary of the object. So we obtain this signature, and for the lower picture we obtain also the lower signature. So it can certainly distinguish the shape of the object. So we could use the signature to distinguish the object. Okay, now we'll continue with the boundary feature descriptors. Now we start with the basic boundary descriptors, which is one is length, and the second one is diameter, major axis, minor axis, and so on. So it means that we could use the length itself as the feature of an object if we could distinguish a collection of objects that we are going to process based on the length itself. If that is not fulfilled, then we have to use in combinations with other features or use other features at all. So again, we could use length only if it is sufficient. If not, we could use diameter only if it is sufficient. For example, we want to distinguish the two objects only based on the size, then diameter could be sufficient. Now we have also major and minor axis. This is something like if this is the object, for example, then the major axis is that line approximately, that is the major axis, and the minor axis is that it has to pass through the center of the object, but this picture is not quite good. And then we could obtain the major axis, the length of the major axis, also the minor axis, the direction of the major axis, and the direction of the minor axis using hoteling or eigenvector transformation. Okay, we could also use basic rectangle or bounding box. So in this case, the bounding box would be something like a box like this one. The sides are always parallel to the major and minor axis for the minimum area. Now we could also use the eccentricity, which is the ratio of the major to the minor axis. We could use we could obtain a feature which is the curvature, which is the rate of change of slope if we traverse a polygonal area. So if the objects are polygons, or we could approximate the object with polygons, then we could use curvature to approximate the or to describe the shape of the object. Now the curvature is the rate of change of slope. So almost like a chain code, but we measure the change of the slope, not encoded using number 0, 1, and so on. And then there is another one, it's called the tortuosity, which measures the twists and turns of a curve. So we will see that one later on. And the for tortuosity, there is a value that measure that. It's called the tau, or we use symbol tau here, which could be calculated as the summations from I equal to n, which is the number of the segment itself, and then the length of the segments. So if we have a slope chain code like before, the curve that we have seen before, then we could measure the tortuosity of that S-like slope using this formula. Now there is an example of where the tortuosity is used. For example, to describe the blood vessels in an eye of prematurely born baby, like in this picture. So the vessels are divided into 3 segments. It is called segment A, B, and C. For each segment A, B, and C, we could describe the blood vessels using the tortuosity. We use n equal to 50 here. Of course, n could be any number. It depends on how small the segments that we use to approximate the curve. And we found a tau, the tortuosity of 2.3770, 2.5 something, and 1.5 something for the curve of A, B, and C. Now we are going to discuss shape number. We will make use of the information for the chain codes that we have discussed before. So let's suppose we have an object, a very small object here, and the chain code for this object is written here. So we start from this point. I will change to red again. We start from this position. We are going east, and the code is 0 here, and then going south. So the chain code is 3, and then going west 2, and going north, and so the chain code is 0, 3, 2, 1. Now if we look at the difference between 0 and 3, then we know that the difference is 3. So I will throw again here, this is the direction for 0, 1, 2, and 3. So the direction, the difference between 0 and 3 is calculated as starting from 0, and we are going towards number 3 and on the anti-clockwise or counterclockwise direction. So we pass through the first quadrant, second quadrant, and fourth quadrant, or we pass number 1, 2, and 3, and so the difference is 3. And then the difference between 2 and 3 is also 3. 1 and 2 is also 3, and 1 and 0 is also 3. So the difference are all 3 here. And the shape number is defined as the minimum of the difference. So we treat the difference in this case as a sequence of numbers, which is 4-digit numbers in this example. And then we choose the starting point such that the new number formed by choosing the starting point will be minimum. Well, in this case, because the difference is 3, 3, and 3, so the shape number is also 3, 3, 3, and 3. Okay, for second object, you could trace this by yourself, and then also for the other object. So that's the basic principle. Okay, how do we actually compute the shape numbers? So let's suppose we have this object, which is like a bottle. And so what we do is we find the major and minor axis, which is drawn as a dashed line here. This is the major and the minor axis. And then we resample the object. Here it is shown the size of the grid to resample. And so finally we obtain the resampled object. Now then we overlay here the direction of the jet code. So if we start with the location is here, I will denote this as a red point. The direction is toward the east, which is there, and that direction. And so the code is 0, 0, 0, 0, okay, followed by 3, followed by another 2 zeros, and so on. And so we obtain this chain code. However, since chain code is affected by rotation, then we have to calculate the difference. Okay, so we calculate the differences like before. The difference between, we could start from the end with the first one if we wish. Okay, so we could start from the end. This is 1 to 0, and the distance between 1 to 0 is 3 here. Okay, so the first result is 3, and then from 0 to 0 is of course 0, and so on. So we obtain the difference. Now from this difference, the shape number is defined to be the minimum size of the numbers consisted of these chain codes by selecting the starting point. Now for this chain code, the starting point, if I choose the starting point this, then I will obtain the minimum number because it starts with 3 zeros. Any other starting point will result in larger than this number. So this is the shape number. And you might wonder why we choose, why we have to change to shape number, not just stop at the difference. Now, the point is that when we would like to find the object on our database or to compare one object with the other, then if we represent the object with shape number, we can compare digit by digit from the beginning to the end. Whereas if we use the difference, the same object rotated differentially would result in again difference. Okay, and that make comparison takes longer. Okay, the next one is what is called the Fourier descriptor. So in Fourier descriptor, let's say we have object looks like a character C in this picture. It consists of x0, y0, x1, y1, x2, y2, and so on. And the number of points are k. So it starts from the indices started from 0 and ended with k minus 1. Now we could represent each point on this two-dimensional space to become a point in one-dimensional space. How do we do that? One is by considering the y and the x and y axis as the real and imaginary part of a complex number. So if you remember how to represent a complex numbers, it consists of the imaginary part, and the real part and the imaginary part. So then each point is becoming only a pair of numbers and imaginary coordinate system. So then again we could represent each point using the Sk, and Sk now is represented in the complex number system as the real part plus the imaginary part. Now we could define what is called the AU by this is how we approximate a curve in a complex coordinate system using the expansion. So The AU, the coefficient, is defined by this formula, which is a summation from k to 0 to from k equal to 0 to k minus 1, yeah, capital K minus 1, sk e to power something like this one. Okay, now we could represent it one using this one. Okay. Now we could approximate that curve by taking samples of P only, P points only. So in this case, P here is less or equal to K. If P equal to K, then it means that we use all the coefficient to represent the shape. And the nice thing about representing with less coefficient, let's say P coefficient which is less than K, is that we can represent the object with less number, which means that the storage in our the storage required to store the object is less, and moreover the computational time to match object represented using Fourier descriptors is also less. Here is an example of the applications of the Fourier descriptor. So on the top left corner, we have an object of the chromosome, human chromosome, which consists of 2,868 points. Which means that if we store that chromosome directly using the boundary information, we have to store 2,868 numbers. Now, if we represent that object using the Fourier descriptor, and we take P to equal only to 1,434 or 286 or 144 or 72 or 36 or 18, then we will have object this. So this object is 50% less storage requirement, and also will use much less computing power to compare this object with the other object. This one is even less, and that one is even less. And if we want to, or if we could distinguish with other object using very small representations like this one, and that is sufficient, then we could use only 18 coefficient. So it's only 18 numbers instead of 2,868 numbers to represent the object. Well, if represent only with 8 coefficient, the shape is quite different. So, and that is the Fourier descriptor, which could be used to save a lot of space to store object using its features, and also improve the computational time. Now, we are going back to the signature that we have discussed before. This is the signature of squares. It has 4 peaks here, there, there, and there. Now we resample this signature in discrete points. Okay, so we have a discrete point like that. And then we could use the statistical moments to describe the object. Previously we described the object using the signature, but now we describe the object using the moments of the signature, and this also describes the object but using much less numbers. So, for example, we could use moment order 1, moment order 2, moment order 3, which is only 3 numbers. Okay. Now, the formula for the moment is written here. The central moment of Z is the summation from 0 to a minus 1, which is the number of the samples, Zi, which is the height, minus the mean, power n. This is the order of the moment. So if it is order 2, then n is equal to 2, and then multiplied by pz, which is the probability. So if we, let's say, normalize the area to become 1, then of course pc is directly substitutable to the equation. Okay, now we continue with the region feature descriptor. Okay, as with the boundary descriptor, we start with the basic regional descriptors. So we could use area if that help us to distinguish objects from other objects in our collections. Let's say we want to categorize or classify X onto large X, medium X, and small X. So we could use area only. We have also compactness, which represent also the object, which should represent the object, and we could use that one if that's enough. We could use the circularity, where A is the area and P is the perimeter. And we could also use the effective diameter, which is 2 square root of A divided by P. So A is the area of the object. Now we could approximate a region by an ellipse. So I have mentioned before and also drawn an ellipse. Now is the application where ellipse could be used to approximate an object. So here we have an object in gray level, and then we could calculate the major axis, and it is shown here. This is the major axis. We could also calculate the minor axis, and the length is shown here by lambda 1 and lambda 2 for the major and minor axis. The direction is shown by the what is called the eigenvector, which is denoted by E1 and E2. Now you could get the formula from the eigenvector transformations or go to the textbook that we are using. And then we could calculate the covariance matrix C, which is this, given this formula. And C is defined by that. Okay, we could use the that features, the compactness, circularity, and eccentricity together to describe a collection of objects. So let's suppose we have 4 objects here. We have a circle, we have a star, we have a square, and we have a teardrop like shape or object. Okay, if we calculate the compactness for the circle, we obtain the compactness is 10 point something. The circularity is 1 point something. The eccentricity is 0.0 something. Whereas for the stars, the compactness is 42, and the circularity is 0.2 something, and the eccentricity is 0.0 something. Now, it means that the 3 features could be used to distinguish very well these four object shapes. If we represent this in vector space model, then we get these representations. So we have the compactness axis, we have the eccentricity axis, and we have a circularity axis. Teardrop, the position is here. It has the value for the eccentricity is 0.8, and the value for the circularity is 0.8 something, and the value for the compactness is something I could not read from this picture. But what we can see is that the object is well separated in this vector space. It means that we could detect each object very well, and so it usually leads to high performance of the method. Okay, continue with the topological descriptors. So the topological descriptors describe an object in terms of the connected component object and the whole. So let's say we have an object on the left. It is one connected component, but it has two holes. And the other one, it has three holes there, and has only one connected component. So of course the value for the descriptor of the topology would be different. And Euler number is one measures that could be used to describe the object based on the number of connected components and the holes. Here we have, let's say for capital A, the hole is 1, the connected component is 1, and so the Euler number is C minus H, which is 1 minus 1 becomes 0. Okay. Whereas for letter B, the Euler number is minus 1. Okay, now we could describe an object based also on the texture. So texture is we are looking at the characteristic of the surface of the object. Now let's suppose we represent an object each by a rectangle. So for the left object, it is represented by this rectangle area. For the object in the middle is by this area, and for the object on the right is represented by that area, which is different texture. So the left one is the superconductor, this one, and then the one in the middle is the human cholesterol, whereas the one on the right is the microprocessor. Now we could use the smoothness, coarseness, and regularity to measure that one. Yeah. So we could use the moment to describe. We might use mean, standard deviation, R, normalized R, the third moment, uniformity, and entropy. The formula is given later. Okay, for the smooth object on the left, which is this one, okay, and the coarse object is this one, this one, and that one is for the regular object. We find that the standard deviations are all different. The means, are also different. The normalized are also different. And the third moment are also different. So it means that these 6 moments could distinguish the object based on the texture. Now, notice that the values range are quite different, so we might have to normalize the statistical measures here. Okay, another one that would be used to describe a texture is called the co-occurrence matrix. So the co-occurrence matrix is obtained using the picture here as an example. So this is the image. Well, if the image intensity range is very high, let's say from 0 to 255, we could reduce or simplify the image into, for example, 32 level or only 8 levels like this one. So after obtaining the simpler version of the image, then we construct what is called the co-occurrence matrix. So co-occurrence matrix record the co-occurrence of a pair of pixel values. Let's say, suppose here, if we scan the image from left to right at this particular position, we run into 6 and then 2. This one is also from 6 to 2. This one is also from 6 to 2. And so we record the events. Okay. How do we record the events? Okay, from 6, we start from here. Okay, run to 2, which is there. So we record one event, and then second event, and then third event. So we have events. Okay. And then for other things, let's say here is, let's say 7 to 8. We have 2 events. Which event is that one? From 7 to 8, this is the event 7 to 8. Another one would be this one. Okay, this is also 7 to 8. Okay, then what could we do with the co-occurrence matrix? Again, we could measure some characteristic of the co-occurrence matrix like before. So here are the formula to calculate. For example, we would like to describe the maximum probability. This is the formula: correlation, contrast, uniformity, or called the energy, homogeneity, entropy, and so on. There are so many descriptor for this texture. Okay, so that means that we could describe an object based on its surface using the co-occurrence matrix as well. Okay, so this is the a picture showing the this is a different characteristic of the texture and also the co-occurrence matrix, how it looks like. Okay, here are some of the computed descriptors: maximum probability, correlation, contrast. Okay, we could see that for this object, the contrast is, well, is high. Okay, you could compare this the value and then distinguish between object number 1, number 2, and number 3. Okay, this different way of characterizing the object. In this case, matches. One is arranged in a regular texture, the other one is almost random, and their appearance in the frequency domain is also different. So basically it means that we could measure the texture either in the spatial domain like we have done before, or in the frequency domain like it is shown in this picture. Now we continue with the moment invariance. So we start with the definition of the central moments, which is an integration. It is a two-dimensional integrations of x power p and y power q, where p and q, p plus q, is the order of the moment. So moment order 2 means that p plus q equal to 2. It could be 0 and 1. It could be 0 and 2, or 2 and 0, or 1 and 1. Okay, if we calculate the moment of the object, the moment itself is not invariant under geometric transformation. For example, the translation. When the object is translated, the moment also changes. The moment value is also changed. So then we define another moment, which is called the central moment. Now, the central moment, and the difference is that there is a minus x average and minus y average, which means that we measure the moment from the center of the object itself. And then the x average is defined here also, which is simply the average, coordinates average. For the digital image though, because the coordinate is discrete and even the pixel values is also discrete, then we could replace the integration with two-dimensional summation over x-axis and summation over y-axis. And then we could calculate mu 00, mu 10, and so on using that formula. And then we have another definition here, which is called the normalized central moments. Eta pq is defined as mu pq. So mu pq has been calculated from there, divided by mu power gamma, mu 00 power gamma. Okay, and gamma is defined as 0.5 multiplied by p plus q plus 1, and for p plus q is greater or equal to 2. Okay, now the moment invariant is this 7 value is a set of 7 values, phi 1, phi 2, phi 3, and so on. So it means that if we are using moment invariance, we describe an object using 7 numbers, which is phi 1 up to phi 7, or in other words, each object as it is described by moment invariance is a point in a 7-dimensional space. Okay, now we look at this picture just to demonstrate how the moment invariance really is invariance under some geometric transformations. This is the original object. Now we see that we reflect this one. We reflect the object to become that one, and then we scale down to become that object. and then we okay, this one is a reflection. Oh, okay, sorry, this one is the translation. Okay, this one is translation, that one is the reflection, this one is the rotation, and this another rotation there. Okay, and see what are the moment invariance calculated from those rotated and translated object. So this is the original image, and these are the values for phi 1, phi 2 up to phi 7. And then you can see when the object is translated, half size, mirror, rotated 45 degrees and rotated 90 degrees. And you can see that the values are almost not changing. Okay, the Harris-Stephen corner detector actually simply describe the characteristic of a corner. Since this is normally describe the corners, not the object itself, unless our object is a corner, then I will just skip for this one. Here just saying that for a corner, then the distribution is like this one. This is for the edge, the distribution is like this one, and for the non-corner and non-edge, the distribution is very small. So by looking at the distribution of the Harris corner descriptors, we could see either we are on a corner, on an edge, or on middle of the object. Okay, we'll skip this one. This one is the application of that. Okay, so now we are moving now to the whole image feature. So this is the last discussion for today. Now, what is the difference between the whole image features and the local features? For the whole image features means that we extract the features from the whole image. So we do not do the segmentation because we don't have to segment the objects. So it is very simple. If we want to get the texture description of the whole image, then we just calculate the texture, either using the method that we have discussed before, or using another method that we have not discussed before. We could measure, for example, the contrast, energy, and so on from the whole image. Now, the boundary element could also be obtained from the whole image. So we are not interested on the boundary of certain objects because we assume that the objects are the whole image. Histogram could also be used to represent the whole image. For example, for image retrieval, which is represented by the histogram, the global histogram, then it means that we are looking at the distribution, color distribution only, and the histogram assumes to be able to distinguish one image from the other. Okay, texture we have discussed before. So basically for the whole image features, it means that we extract the features from the whole image, so makes life simpler because we don't have to segment and so on. Okay, so this is the end of our meeting for today. Hope you are staying healthy and in good health.